Good evening, everyone. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics at Australian National University, and this seminar forms part of their 2025 series of seminars organised on behalf of the Australian Institute of Physics. As many of you would be aware, we started this series of seminars with the intention of promoting important ideas in theoretical physics to the physics community in Australia. One of the disadvantages of living in Australia is a long way to get to overseas conferences, and it's expensive and so forth. So this provides an opportunity for people to stay in contact with what's going on overseas. We've been operating now for 4 years, and we've had some of the best theoretical physicists from around Australia and from around the world to give excellent talks. So if you wish to keep up to date with what's going to happen in future seminars, you're more than welcome to join the Theoretical Physics Group of the Australian Institute of Physics. You do that just on your AIP login page if you're a member of the AIP. And if not, then consider joining the Australian Institute of Physics. When you go in there, you'll see the link to the topical groups, and the Theoretical Physics Group is listed there. Tonight's speaker is Pieter Claeys from the research, who is the research group leader for the study of the physics of complex systems at the Max Planck Institute. I think you started that group, didn't you, Peter? Is that right?
So I'm currently looking at the Max Planck Institute for the Physics of Complex Systems, and my group is Dynamics of Quantum Information, which I started here as part of the broader institute.
As part of the broader institute. Okay, thanks.
Yes. Sadly, I did not start this entire
institute. You didn't start the entire Max Planck Institute either. No, I know. So Peter did his PhD research, as you might have seen in his abstract, from Ghent University in Belgium and the University of Amsterdam in Netherlands. After obtaining his PhD in 2018, he did postdoctoral research at Boston University in the United States, and in the United Kingdom, the University of Cambridge, before starting his research group, which, as he just clarified, is the physics of complex systems in Dresden, in Germany, from whence he speaks to us this evening. His research group studies a range of aspects of quantum many-body physics through the lens of quantum information. His research interests including quantum chaos and geometry, integrable systems for K-dynamics, and quantum circuits, which is what he's going to talk about tonight. The particular topic that he's going to address tonight is a really interesting topic. It's the topic of dual unitary circuits. And what's so interesting about these things is that they facilitate exact calculations of thermalization problems, scrambling, entanglement dynamics, and can inform us even somewhat counterintuitively about the dynamics of chaotic systems and so forth. As Peter will explain to us, the term dual unity refers to an underlying space-time duality in the model, which, amongst other properties, gives rise to the very interesting class of models that I just mentioned, the ability to provide exactly solvable solutions, which are for systems that are provably chaotic. So to tell us a lot more about this fascinating subject, Peter's talk tonight is entitled Dual Unitary Circuits as Minimal Models for Quantum Many-Body Dynamics. Thanks, Peter. Over to you.
Well, thank you very much. I already very much appreciated the invitation to give the seminar, and I appreciate it even more after this very nice introduction. So I'm very glad to be able to talk a bit about dual-unitarity, which has really been one of my main research focuses in the past years, and which I've really started focusing on the moment I moved to this Max Planck Institute here. So before I actually get to the bulk of my talk, I first would want to acknowledge the collaborators with whom I did all of this work. So I'm going to be talking about some research which was done by Michael Ram, who is my first PhD student here at the Institute, Suhail, who's a very talented postdoc here, Giuseppe, who was a postdoc here and is currently faculty in Lisbon, and Austin, who was my postdoc supervisor at the University of Cambridge, where I also got interested in circuit dynamics more generally. So I want to study dual-unitary circuits, but I first want to briefly zoom out as to why we might be interested in dual-unitarity and studying these kind of models. And the main reason that is we have these quantum many-body systems, and we want to understand how they relax to equilibrium. We want to understand the dynamics of these systems. We're not classically, if we study dynamics, we can understand this through the lens of, say, statistical mechanics, thermodynamics. And typically what we see is that if I take a classical system, say a glass of water, and I prepare this in some initial state, or I slightly perturb it locally, for example, by injecting like a few drops of blue ink in here, the system is going to evolve. There's many different water molecules. It's very complicated dynamics, but we see that if we just look at the overall system, we end up with some kind of steady state where the ink has spread throughout this entire system and we have some uniform mixture. And of course, we don't ever describe this on the level of the molecules, but rather we find some thermodynamic description, which tells that the equilibrium state is a maximum entropy state. And essentially, we want to understand the same kind of phenomena in the context of quantum many-body systems, where, however, if I want to study a quantum many-body system, the relevant dimension of the Hilbert space tends to grow exponentially with the number of particles. So there's really no hope to generally understand what's going on there just using, say, numerical simulations. So that's why I want to move to dual-unitary circuits, which I can really think of as being minimal models for many-body quantum dynamics with two key properties, namely they're local, as in the dynamics is generated by local interactions, which is what we generically expect in physics, and it's unitary, which is what we generically expect for closed many-body quantum dynamics. And I've just thrown a bunch of references in here. So this field really started in 2019, although arguably some results already appeared in the literature early. And there's been many different results on this in the past few years. So one of the few reasons that people are interested in this, as they've already mentioned very kindly, is that these models are exactly solvable. And they allow us to make exact statements and do exact calculations on, say, thermalization. So how these systems equilibrate, how do we get to a steady state? We can study scrambling, so how this initial local information gets distributed non-locally. And we can make statements about entanglement growth, so how does, say, entanglement build up between different subsystems in a large system. But more than that, typically whenever we can make some exact statements, it's because these systems have some kind of underlying structure, for example, integrability or extra conservation laws, which prevent these systems from being ergodic or from being chaotic. Here is very much the opposite. These systems are actually maximally chaotic, and even more remarkable is that we can use them to make analytical statements about random matrix theory, which is essentially the main lens through which we try to understand quantum chaos currently. And one of the physical properties that underlies both of these properties is that these dual-unitary circuits have so-called maximal entanglement velocity, by which I mean they generate entanglement at the fastest possible rate. They effectively generate randomness and correlations as fast as you possibly can imagine. So now the bulk of my talk. I first want to give a brief overview, and I'm first going to be introducing the self-dual kicked Ising model. So rather than introducing dual-unitarity in full generality, I want to focus on a specific model, analyze that model in detail, show how you can make some statements about exact solvability, focusing on correlation functions, how you can make statements about emergent randomness. Then I want to briefly discuss how this fits within the broader framework of dual-unitarity and dual-unitary quantum circuits, before I briefly highlight some recent developments which try to extend the notion of dual-unitarity while still allowing for exact predictions. So first topic of my talk is the self-dual kicked Ising model. So it's very simple, or rather I should say, let's start from a very simple setup. Maybe you consider a standard one-dimensional lattice of spin 1/2 degrees of freedom. So I have a one-dimensional lattice, and on every lattice side, I have, say, a qubit or a spin 1/2. And I'm going to be evolving this in time using Hamiltonian dynamics, where I alternate two types of Hamiltonian dynamics. So in that sense, this corresponds to a Fouquet model. And I'm going to later tell you how you can actually reformulate this as a quantum circuit. So we're going to be alternating some classical Ising dynamics with some quantum kicks that create a superposition. Now, what do I mean by that? So I have two Hamiltonians, Hi, which is the Ising interaction. And you can see that I have these nearest neighbor interactions, which are just Ising interactions, or Ising interactions, I should say, since I moved to Germany, where you have these Pauli Z matrices on neighboring sides, and you basically have a sign plus or minus j, depending on whether your spins are aligned or anti-aligned. I can have some longitudinal field, which is set by Hj, which can possibly be disordered. So I'm going to let my system evolve with this classical Hamiltonian. which if I start from a state in the Z basis, this is just going to add some global phase. So I don't create any kind of superpositions in this way. But then what I'm going to be doing, I'm going to alternate this classical evolution with a quantum kick, where I basically apply a Pauli X matrix to every side with some kick strength B. And if I do that, I can create some periodic dynamics by periodically alternating between these two evolutions. And I effectively have discrete dynamics, where every discrete time step corresponds to one application of these kicks and one application of these easing phases. So now I'm going to be looking at if I take some initial state, say a state with all spins down, now let this evolve in this discrete time, what is this going to look like? And in general, this problem is exponentially hard to say anything about, but we can focus on the special case where the model is dual-unitary, in a way that I'm going to be explaining in the next slide, which happens to be when this easing strength J and this kick strength B, both of which I've observed the relative timescales for this dynamics, equals pi over 4. And the reason why this is pi over 4 should become clear shortly. The interesting thing is that this fixes the strength of the easing interactions and the kicks, which you can think of as a transverse field, but you still have a longitudinal field, which also actually gives you quite a lot of freedom to tune the dynamics. So the way to understand why this is dual-unitary is actually by moving to a graphical language, which is the graphical language of tensor networks, and in this case, which is also very closely related to the graphical language of ZX calculus, where I'm going to be finding some graphical way of representing both these easing phases and these quantum kicks in such a way that I highlight the fact that the dynamics in space is really exactly the same as dynamics in time. So I'm going to be introducing a graphical notation for, say, single-site operators. For example, here I have my e to the minus ibx, which is I apply the quantum kick to a single site, to a single spin 1/2 degree of freedom. So this really just corresponds to a 2x2 matrix. I label my basis states by S1 and S1 prime. So both of these can take values either spin up, spin down, or 0 or 1. And I represent this matrix by this blue square. And I represent the matrix elements simply by these legs, or rather, I take the indices, which fix the elements of this matrix, to be corresponding to these legs. So if I fix matrix element S1, S1 prime, this corresponds to labeling this leg by S1, this one by S1 prime. Now, I can do the same thing for these phases. Now, this is a two-site operator, because I have a nearest neighbor interaction. So if I have an interaction between site 1 and site 2, so here I have e to the minus ij easing interaction, here I have the longitudinal field, where this should be a capital Z. This is now going to be a 4x4 matrix. So this acts basically on two copies of my local Hilbert space. So I can have S1 for the first Hilbert space, S2 for the second Hilbert space. And again, now this is a 4x4 matrix. I have 4 basis states, which correspond to choosing S1 and S2 to be either 0 or 1. So we have 0, 0, 0, 1, 1, 0, 1, 1, or the same thing in terms of spin up, spin down. And I can represent this in this way, where now this basically has 2 indices coming in, 2 indices coming out. And I've represented this in a very suggestive way, that it seems that the way I write this down is somehow related to this blue square in here. And this can actually be made very explicit, which also necessitates basically the focus on the dual-unitary point, where I choose these black circles here to be essentially delta tensors. So here I have a black circle. It connects 3 different indices, S1, S2, S3. So actually this fixes all of these indices to be the same, and it applies an overall phase, depending on whether this is spin up or spin down, whether this is 0 or 1. And for example, if I look into what's happening to this easing interaction, well, S1 and S2, these are product states in my Z basis, which means that if I act with this operator on this state, I just apply some overall phase, but I don't change the state of my system, which means that these matrix elements are only non-zero if S1 equals S1 prime, S2 equals S2 prime, which is exactly what you see here. S1 needs to equal S1 prime, S2 needs to equal S2 prime. And then for every choice of S1 and S2, I apply some phase, and I just store this phase in this blue square in this matrix. And at the dual-unitary point, this actually exactly corresponds to what you have for this kick here. Because if I look into the matrix representing this kick, it's e to the minus I pi over 4x, which if I write this down in this way, looks like this so-called Hadamard matrix. The matrix elements are 1, minus I, 1. And this matrix has a very special property that it's unitary, which it has to be because it generates unitary evolution. But also all of its matrix elements have the same modulus, so they have the same absolute value, which means that all these matrix elements, I can just interpret these as phases. So I can now think of this blue square as either representing the application of my kick, which creates a superposition, or storing the phases I apply when I consider the easing interaction between two nearest neighbor sides, which are again phases. And the fact that I can choose this longitudinal field freely basically corresponds to the fact that I can choose these phases in this delta tensor freely. So I hope this is clear. In any case, stop me if I'm saying anything that's unclear. So what is kind of highlighting is that these easing phases and these quantum kicks are in some way interchangeable, which is already suggestive just on the level of looking at these single matrices. So I have either these 2x2 matrices, which are unitary store phases, or these 4x4 matrices, which are diagonal, and they have these phases on the diagonal. Let me now move to actually the many-body case, where we can now use this to show that the full many-body dynamics actually has the same duality between space and time. So I'm going to periodically alternate this classical easing dynamics with quantum kicks. So I start from some initial product states, say S1, S2, S3, up to SL. Again, these can all take values either 0 or 1. And now I want to evolve this in time. So, oh, sorry, wrong direction. I first apply this classical easing dynamics, which again, this Hamiltonian is diagonal. This just acts with some overall phase on my state. It doesn't change it. So basically the state S1 here is the same as the state here. State S2 here is the same as the state here. I just apply some phase depending on the value of S1, S2, S2, S3, S3, S4, and so on. So this is the easing dynamics. Then I apply these kicks. And these kicks are now single site operators. So for example, here on S1, I now create the superposition. I do the same thing on S2. I do the same thing on S3. Now this corresponds to a single discrete time step. So a single layer of my easing phases and my quantum kicks. And now I can keep doing that. And I should also mention, since these are delta tensors, now I've kind of extended this notation where essentially any dot connecting an arbitrary number of legs fixes these to be identical and applies some overall phase, which is really just, I can take these three-side delta tensors and simply merge them. So I have my single step evolution for my initial product state. I can keep doing this. And essentially, I generate a circuit that looks something like this. So this is here illustrated for 3 time steps. So 3 applications of this layer of easing phases and 3 applications of this layer of kicks. And you can see that this is simply a square lattice. And if I look at this for the horizontal direction, so from the bottom to the top, or along, the vertical direction from the bottom to the top, or the horizontal one from the right to the left, these look essentially interchangeable, which means that this dynamics is actually dual-unitary. So you have something that's unitary in both space and time. So let me be a bit more precise. So I look at my total evolution operator, u to the power t. I can look at these matrix elements. So this is simply, I have my many-body evolution operator. I look into my many-body state and my many-body basis. I have that is unitary in time simply by construction. I've chosen my dynamics to be unitary, and I have this unitary evolution operator, which is basically my Floquet operator, which is the easing phases followed by these kicks. However, I can also look into the other direction, and I can see that if I now act basically from the left to the right or the right to the left, so along the spatial direction, this looks completely identical. So the evolution that's kind of generated in the system, if I look at the bulk, it's identical if I look along the spatial direction or the time direction, which means that the dynamics is also unitary in the spatial direction, which is exactly what people understand the dual unitarity to be. So I hope this is clear. If not, again, please stop me. And this might seem somewhat, just a curious observation, but actually demanding that you have unitarity in both space and time immediately leads to both exactly solvable and quantum chaotic dynamics. So let me first give the simplest argument as to why these models are exactly solvable. And I'm going to be focusing on correlation functions. And for correlation functions, dual unitarity actually has a very striking effect. So if I look at correlation functions, so I have some operator O, say at site X, I evolve this in time, so U dagger O, U, and I look at the correlation between some operator O at some different site Y. I create some correlations that are going to depend on the distance x minus y and the number of time steps I've evolved my initial operator for. And, oh, sorry. If I take these correlation functions, where here I basically take the trace, which is the expectation value with respect to the maximum mixed state, which is the natural state in these circuits because you don't have any kind of conservation of energy. Then, if I look at these correlation functions, they're identically zero almost everywhere, apart on the edge of the causal light cone, which is exactly when the distance between x and y is exactly equal to the number of time steps. So the remarkable thing is also that, okay, not only do these correlations vanish almost everywhere, but they also can be exactly calculated on the edge of this causal light cone for arbitrary long times. So if we look at these kind of correlation functions of the form U dagger O, U, O, we can calculate this exactly in dual-unitary circuits, whereas in generic circuits or generic many-body dynamics, this is something that's really exponentially costly to calculate. And I should really highlight this very nice paper by Bruno Bertini, Pavel Koch, and Tomasz Prosen, where they observed this and kind of gave the argument as to why this is the case. And it's a very neat argument, so I briefly want to repeat this here. So if I want to look at how these correlation functions behave, I can move to the Heisenberg picture, where I take my initial operator O at site x, and I evolve this in time. So this evolves in time as U dagger O, U, which graphically I can now represent basically in the form of this diagram, where you can see here at the top, I have taken my original circuit, now for 2 time steps, so 2 layers of Ising phases, 2 layers of quantum kicks. I take my operator, which I take to be a single site operator. I represent this by this white circle, which again, this is just representing a matrix that only acts non-trivially on a single site. And then here at the bottom, I've basically constructed U dagger, which is just I take this circuit here and to simply take the Hermitian conjugate of all of the different matrices in there. Now, what we can do is we can actually try to identify places which we can use unitarity to simplify this circuit. Because actually we know that this gate here, for example, so this operator, it's simply at some phase, depending on the value of these 2 states. But here I basically have the unitary conjugate, sorry, the Hermitian conjugate of this phase. So essentially these 2 are going to cancel with each other because this is just the Hermitian conjugate of this one. Same thing here, same thing here, same thing here, same thing here, same thing here. The only place where I can't use unitarity to simplify this circuit is basically here. Essentially, this operator here doesn't allow me to simplify the multiplication of this one with this one. So let me just illustrate this. So if I now just use unitarity to get rid of all the possible phases I can do in this first layer, in this first time step, I can essentially remove these phases here, here, and here, and here, to simplify my circuit in this way. So I've already removed quite a few of the actual unitary evolution operators acting on sites outside of this causal light cone of my operator O. Then by doing that, I've actually introduced places where I multiply this matrix with this matrix, which is its Hermitian conjugate. Same thing here, same thing here, same thing here, same thing here, and so on. And I can again now use unitarity to cancel these with each other. And I can simplify my circuit to something that looks like this. And by doing this, now I've reintroduced new places where I can cancel phases against each other. And if I do this, and I again cancel unitaries with each other, I essentially end up with something like this. So what this is telling me is that the support of my operator, basically, it acts non-trivially everywhere within this hourglass shape. It acts trivially, so as the identity, everywhere outside of this hourglass shape. So I have an initial operator, which acts non-trivially on a single site. After a single time step, this acts non-trivially on 3 sites. After 2 time steps, this acts non-trivially on 5 sites, and so on. So the support goes linearly in time, which is basically your operator becomes more and more complex. It spreads out. But this does so with a finite velocity, which means it's completely trivial outside of this support, which means that all correlations between this initial operator and any operator that's outside of the support of this operator should trivialize. And if I take this operator to be traceless, this means they should vanish. So if I look at correlation functions, from unitarity, I have that they should exhibit a causal light cone in time. And dual-unitarity then additionally imposes a causal light cone in space. So again, I look at these correlation functions here. I represent this graphically in kind of this space-time diagram. Just using unitarity, I can argue that all correlations, basically outside of this light cone, outside of this hourglass shape, should be identically zero simply because there's no way for these operators to be correlated, simply because of the geometry and the unitarity of the structure. I can also use dual-unitarity, however, so the unitarity in space, to reverse this argument and argue that if I look into a light cone along a spatial direction, all correlation functions also vanish there. So correlation functions shouldn't just decay or shouldn't just be identically zero inside of this region. They should also be identically zero inside of this light cone, which is the causal light cone along the spatial direction. It's exactly like the inside of the causal light cone along the time direction. So this might seem discouraging because correlations vanish almost everywhere, but the one spot where these actually are not enforced to vanish either from unitarity in time or unitarity in space is exactly on the edge of this causal light cone or on these light rays, where basically this distance between your initial operator and the other operator is exactly equal to the number of time steps. So this is kind of the argument as to why these correlation functions should be identically zero everywhere, except on the edge of this causal light cone. And I'm not really sweeping anything under the rug here. This is exactly how this proof works. And then what we have is that the correlation functions are almost zero. They're zero almost everywhere in your space-time, except for the edge of this causal light cone. But actually, we can use some graphical manipulations to show that if I look at these correlation functions on the edge of the light cone, well, let me quickly return to this here. If I want to calculate the correlation function between this operator here and an operator here, I take the trace and I can again use unitarity to get rid of almost all of my gates. I can express this expression for this correlation function on the edge of the causal light cone in this way, where I've kind of removed almost all matrices except for the ones that are actually just along this light cone. And this is something that if you just write this down as kind of matrix manipulations, you can evaluate exactly. And for example, if I focus on this Kieft-Ising model, I take some longitudinal field with strength h, and I'll calculate this correlation function. So I basically just evaluate this for my operator to be sigma x. I evaluate this and I basically just get cosine 2h, where h is your transverse field strength, longitudinal field strength, to the power of t. The one thing that I want to illustrate here is that these correlation functions decay exactly to zero at long times if your h is not in such a way that cosine 2h equals 1, which actually this single point corresponds to the integrable case of this Kieft-Ising model. So in generally, for generic values of this transverse field, this longitudinal field, the dynamics are going to be ergodic, and the correlation functions are going to decay to zero. However, if we would choose different kinds of structures, we can actually realize a very rich variety of dynamical behaviors, ranging from ergodic to non-ergodic, and with correlation that either oscillate or decay in time. So this clearly it's a very nice observation. This has also been observed experimentally, and so it's not just some theoretical curiosity. So, for example, Quantinuum, then Honeywell, realized this Kieft-Ising dynamics in the trapped ion quantum computer, in a way that I'm going to be making explicit in a few slides. And they looked basically at these correlation functions in space-time, using some trick to which they basically could calculate these correlation functions near the edge of the causal light cone using only 11 qubits. And so they did this for the dual-unitary case, which is basically the top. So if you look at the top column, on the left-hand side, you have theory. On the right-hand side, you have experiment. They look at the correlation functions, and so they're not exactly zero outside the light cone because of precise details of their implementation. But you can see that these correlations, they spread out with this maximal velocity, which is basically the distance equals number of time steps. On the left-hand side, you see the theory, and it agrees very well with experiment. And so you recover this dual-unitary behavior, where you have the correlation functions vanishing off the light cone, and on the light cone, they go to zero exponentially. On the bottom, they compare this with something that's not dual-unitary, and simply looks like a bit more of a mess. You don't have these very clear signatures that you expect for dual-unitary dynamics. So a more recent experiment, which appeared on arXiv last December, was essentially a slightly more direct realization of this Kieft-Ising dynamics, where collaborators were basically people from IBM Dublin, together with their collaborators, actually realized this Kieft-Ising chain for up to 91 lattice sites, which is very impressive, and explicitly calculate this correlation function. So they also observed experimentally that these vanished inside this causal light cone, and they explicitly measured the correlation functions on the edge of this causal light cone. And they did this for various values of this longitudinal field. So for 0, in which case these correlation functions don't decay, you simply have the transfer field Ising model, which you can solve using mapping through field fermions. So correlation functions don't decay. So every row here corresponds to a different value of this longitudinal field, so ranging from h equals 0, h equals 0.05, h equals 0.1, 0.15. And the different columns correspond to different lengths of your chain. So the quantum processor they have has an architecture that looks something like this. So ideally, you want to identify some kind of one-dimensional chain in there in order to be able to use these unitary results. So the chain kind of corresponds for 51 sides to this thing here, snaking around, for 71 sides to this one, and finally for the largest they consider for 91, they use almost all of your quantum processor. Then they just experimentally measure these correlation functions, and you can see in all cases, away from h equals 0, that these tend to decay exponentially. And what they actually observed that, okay, if you just do the naive measurement, you find exponential decay that's significantly faster than what you would expect just from theoretical predictions. Which makes sense because these quantum processors, they're very noisy, so things tend to decay much faster than you would expect. They can actually do some noise mitigation by essentially benchmarking against what would happen in the h equals 0 case, where you don't expect any decay. And if they do this noise mitigation, then you basically recover these dashed lines or these crosses here. And you observe something that gets very close to what you actually expect theoretically. So it's very nice that we have these theoretical predictions for the dynamics of correlation functions in unitary circuits, which again, there are still many body systems. So in general, it's exponentially hard to calculate these correlation functions, but we can calculate them, we can make theoretical predictions, and people can measure them in experiments with very nice agreements. So why it's actually possible to do these kind of experiments in quantum processors so directly, either in these strapped ion quantum computers or in IBM's quantum computers, is that these kicked Ising models are actually very natively realized as quantum gates. So if I look at digital quantum computers, basically the way they act is you have some lattice of qubits, and then you act on these with gates, which are just really unitary transformations on two sides. But then you can actually choose these two-side gates in such a way that these are just dual unitary, which I mean I have some two-side gates, for example, illustrated here. Basically, these two are my two lattice sides or my two input qubits. And the unitary evolution is just a unitary transformation, which is the evolution in time. So basically, these gates need to be unitary in this direction. But I can also choose my two-side gates in such a way that they're also unitary if I choose these two as input and these two as output. And actually, the entire kicked Ising model can be mapped back to some kind of quantum circuit constructed out of these two-side gates, where each two-side gate is unitary either using these two as input or these two as input. And these kind of gates, they're directly realized in these processors. So there have been experimental realizations of unitary quantum circuits, both, for example, here in Google Sycamore processor, where they experimentally probed scrambling, which I'm not going to be talking about today, or in IBM's processor, which is exactly where this is experiment that measured these correlation functions. So with that, I kind of want to highlight that we get these exact results for correlation functions in models that can be directly realized on quantum computers. However, that's not the only thing. So I mentioned that these systems, they're both chaotic and exactly solvable. So far, I've only talked about the exact solvability. So you might also think that, okay, maybe the dynamics in these systems is just very trivial. Maybe my operator just kind of moves along the light cone and nothing else happens. But it's the opposite. Things are very complex the moment you kind of move away from these correlation functions. And we can talk about this, for example, in the language of emergent randomness or emergent complexity. So before I continue, any questions about anything I've said so far?
Well, I think it's pretty clear, actually. It's good.
Okay.
Yeah.
Perfect.
I want to ask you a question a little bit later about the relationship, if there is one, or what type of relationship you can get between this and, for example, random matrix theory. But I get that's getting a little bit beyond your topic, perhaps, but that's something that
is, I would say, my next slide. So I very much appreciate.
Oh, there we go. I'm anticipating. Carry
Yes.
on.
We did not agree on this beforehand. Yes. So the way that we describe this emergent randomness and quantum chaotic behavior in many body systems, where typically if you want to describe chaos, say in a classical setup, you look at basically how you can define a Lyapunov exponent. So if you have some exponential sensitivity to perturbations. However, it's not something you can reasonably define in quantum systems because there's no notion of trajectories. And also because of Heisenberg's uncertainty principle, you always have essentially uncertainty on your trajectories. So the way that people describe quantum chaos and also the way through which we understand thermalization is by saying that if I look into these unitaries, which generate our many-body dynamics, in a lot of ways, they look like random matrices. And basically, the complexity that you would expect from exponential sensitivity in classical dynamics is translated to basically having this uncertainty and this randomness from random matrix theory. And I would say like one of the first analytic results on unitary circuits, even before people were aware of the term dual-unitarity, was to show that if I look into this kicked-Ising model and look at the unitary evolution, I can look at its eigenspectrum, and I can look at so-called spectral form factor, which basically I have trace u of t, I take its absolute value, I square this, which I can express in terms of the eigenphases e to the I phi of this unitary in this way. This encodes correlations between the eigenvalues of the unitary evolution operator. And if I had a random unitary matrix, actually its eigenphases don't behave as random variables. They're actually very correlated because they need to originate as eigenphases from the same unitary. And so we can do the calculation and check what we get in this unitary matrix. So this very structured unitary evolution operator for the kicked-Ising model with what we get from just a random matrix. So U just random. And if we do this for random matrix theory, we expect essentially linear growth of the so-called spectral form factor, which is basically just this full line here. And then we can do the calculation for the unitary circuit, and we can actually get analytic proofs that this also reproduces this random matrix theory prediction. So here you also get this linear growth. I should say the spectral form factor is not something that is self-averaging. So if you actually want to calculate this, you also need to introduce some kind of disorder average, where this disorder can really be arbitrarily small. So here we have the advantage that we can have this longitudinal field, and we basically just add some disorder there and average over this. And we see that as you do that, and I choose this disorder variance to be, say, sigma, as I do this averaging, I basically very nicely recover this linear growth, which indicates that the spectrum of my unitary evolution operator is essentially indistinguishable from the spectrum of a purely random matrix. So despite the fact, or rather, because of the fact that these correlation functions vanish everywhere, this kind of indicates it's very chaotic. And so we can exactly solve this. But we can also say that actually this unitary looks almost indistinguishable on the spectral level from a random matrix. So this is now, if we just look at the spectral behavior. But if I go back to what I talked about in my introductory slide, I'm really interested in basically how some initial state of my system evolves in time. So for that, I don't just want to look at, say, the spectrum, which it gives you a lot of information. It's also one of the ways that people try to quantify quantum chaos. But fundamentally, I'm interested in how some initial state, some initial operator evolves in time. And if I can actually make some argument that at long times, this state satisfies some kind of maximum entropy principle. And so because of that, we can actually see what happens in the quantum case. If I now want to translate this picture I showed you of this glass of water equilibrating, ending up with some maximum entropy state, which is basically locally, this looks in equilibrium. Quantum mechanically, if we think of what's happening, it's actually somewhat different. Because we have the Schrödinger equation, or rather we have our unitary evolution for any closed quantum system, where if I have some initial state, at time t, my state is just some unitary transformation of my initial state. So the state itself can actually never equilibrate, because any unitary transformation, it's unitary, I can just invert it. So if I know my state at time t, and I know my unitary evolution, I can always recover my initial state. So the state itself is never going to go to some kind of equilibrium steady state, but rather what's happening, okay, so because unitary is reversible, I can always get my initial state from my final state. Rather what's happening is that if I start from some initially structured state, for example, this blob of ink in my glass, or say a spin state in which all spins are spin up, or more generally say any kind of product state or any lowly entangled state, this is a very structured state. But through the dynamics, entanglement builds up, and effectively this state becomes more and more complex, which is also something that was kind of apparent in this operator spreading picture or this operator growth picture of an initial operator. And at long times, this state essentially becomes indistinguishable from a maximally random state, where with maximally random, I essentially mean a high random state. And then, okay, the state keeps evolving, but at any time, at late times, it essentially just looks purely random. And I can replace this expectation value of my time evolved, of my operator in my time evolved state, or my time evolved operator in my initial state, by just replacing this by purely random state. And if I take the average of this expression over high random states, Well, this exactly gives me some equilibration, because essentially for any high random state, or rather for most high random states, this expectation value is just going to be identical to simply the trace of the operator, normalized by the dimension, which is essentially saying that if I look into the eigenbasis, or essentially any basis for the operator, and I calculate this trace, well, I simply calculate the diagonal expectation value, and I take the sum. So I can really think of this expectation value with respect to a high random state, just kind of giving you the average expectation value that you would expect in any basis. Now, this is important because essentially what we're seeing here, the steady state value, it doesn't depend on the initial state anymore. So if the state is sufficiently complex, I get this higher expectation value, simply the trace. And even though this state keeps evolving, at every time step, it's essentially indistinguishable from a random state, and I produce essentially this equilibrated value of my observable. So the important thing here is the state is not equilibrate, rather it becomes more and more complex. But any operator whose expectation value evaluated with respect to this state is essentially going to appear as if it's equilibrated. So if you want to understand this, we can now ask, okay, I look at my dual-unitary dynamics. How close is the state I get through doing my dynamics to a purely high random state? And this is a question that actually also underlies these tests of quantum advantage, or rather quantum benchmarking in quantum computers, where people are also trying to quantify how well they can prepare a high random state, because high random states are very entangled and they present a very useful resource for quantum computing. So you can ask, how close is a state to a purely high random state? And again, we're going to be doing this on a statistical level. So I take my state, and I basically look at its component in some basis, which is my computational basis. So again, S1, S2, SL. These can all be either 0 or 1, spin up or down. And I basically look at how these different probabilities are distributed. So again, I have my state. If I want to know the probability of having some kind of bit string or some specific product state, simply taking this overlap between this evolved state and this product state, I take the probability, so I need to square the absolute value. And if this is a random state, I can't say anything about any specific probability. But rather what you can say is you can look at the specific distribution of probabilities. So basically, I take my state, I calculate all of these overlaps, I get the corresponding probabilities by squaring them, and I simply plot a histogram of this. And for a high random state, this gives rise to this celebrated Porter-Thomas distribution, which here looks like this, which is a fancy way of just saying it's an exponential distribution. If I have a random state in some n-dimensional Hilbert space, which in this case, n is basically 2 to the power L, where L is my number of lattice size, these probabilities are distributed in this way, which basically you have a lot of probabilities that are very small, and then becomes increasingly less likely or exponentially less likely to find larger probabilities. This is really telling you some statistical information about your quantum state. And I should also say this is very interesting, or rather you want to look at this in a quantum context, because kind of if you would look at a classical state or any kind of classical randomness, this would look very different. You could get, for example, some kind of Gaussian distribution or some uniform distribution, but this exponential distribution is what you expect for a highly entangled high random state. So we want to compare, if I have my state, how much this actually reproduces the so-called Porter-Thomas distribution if I look into this distribution of probabilities. Also, before I continue, one other way of thinking about this is basically you can look at how this state psi is localized or delocalized in your computational basis. Because essentially here you look at the statistics of basically where this is localized in your full Hilbert space. So let's return now to the unitary case. And actually we can say something specific here. And we look at the dynamics of, say, some initial product state where I prepare everything in, say, 0 or spin down, and let this evolve in time. And I look now basically what happens if I do this measurement again in my computational basis. So S1, S2, S3 are all either 0 or 1. And if I do that, well, after a single time step, if I look at my probabilities, or rather these overlaps, I get something where basically these are all identical, which is basically I start from a product state. And if I apply these kick once, basically if I act with the kick on the side 0, I get an equal weight superposition of 0 and 1. So for a single time step, I basically just create an equal weight superposition of all my possible states in my Hilbert space. So basically all these probabilities, they're identical. It's a very structured state. Second time step, I get a uniform distribution, like a box distribution. If I calculate these overlaps, which is still, it looks somewhat more random, but still very far away from this Porter-Thomas distribution. And I can keep doing this. And I can see that after 3 time steps, so I take my time-evolved state, look at all these components in my computational basis. This again begins to resemble the Porter-Thomas distribution. And essentially, after say 5, 6 time steps, the distribution I end up with is almost indistinguishable from Porter-Thomas distribution, which is, again, I should probably have told us, this is this dashed line here. And this blue line, these blue histograms are just what I see if I do this numerically for a system of 14 sites. So we get this Porter-Thomas distribution, which indicates that our state looks random, also basically on the level of these components. So our unitary evolution operator looks random if you look at the eigenphases. Our evolved state looks random if you look at basically its components in this computational basis, despite the fact that it's very structured dynamics. Because at no point did I introduce any kind of randomness here. I know my state, I can undo the unitary dynamics, and I would get my initial product state. So it's a very natural question, how does this kind of randomness arise under chaotic many-body dynamics with a very structured Hamiltonian, or with a very structured unitary? And for that, the observation that we, instead of looking at what's happening in the time direction, we need to look at what's happening in the spatial direction. Now we can actually make some statements about how our evolution in the time and the spatial direction acts to actually show that we get some randomness there. Let me be a bit more precise. And this actually is based on some very nice ideas in this paper by Wenwei Ho and Sung-Won Choi, this paper by Stephen and co-authors, which tells that if I want to look at kind of any component of my time-evolved state, so I just look at one fixed component, S1, S2, S3, SL, for example, 1, 1, 0, 1, 1, something like that, I can interpret this actually as a measurement-based quantum computation along my spatial direction, which sounds very fancy, but the basic idea is very simple. I just look at what happens along my spatial direction. So I've already mentioned before, I have dual-unitarity. And actually for any choice of state 0 and 1 here, 0 and 1 here, this purple transfer matrix, it's actually a unitary. So I have unitary in my spatial direction. And I could, for example, introduce some kind of boundary conditions, which I've just slightly extended my delta tensor. I'm not doing anything here. So I can think of this, I have some left boundary condition. I apply a unitary, which is set by S1. Then I apply a unitary, which is set by S2. Then I apply a unitary, which is set by S3, and so on. And finally, I apply a unitary that's set by SL. And I look at the final matrix element with respect to some other boundary. So basically what I have some matrix element of this product of unitaries in my spatial direction. I look at one specific matrix element of these unitaries. But the important thing here is that whenever we're actually sampling over measurement outcomes, this is basically sampling over the different states S1, S2, S3, SL. Essentially, every state here corresponds to a different sequence of unitary matrices being multiplied. In the thermodynamic limit, basically that the number of unitaries I multiply goes to infinity. Essentially, I just have a random sequence of unitaries, which every measured outcome, basically every S gives me either unitary U of S1 or U S1 equals 0 or S1 equals 1. So if I sample all these possible states, I'm essentially sampling all possible different products of unitaries. And we can show that these are actually, these form a universal gate set, which basically only means that if I multiply an infinite number of these together randomly, I just get a high random matrix. And then I can just say that, okay, when I do this averaging over different basis states, so I look at these statistical properties, I can just replace the average there by an average over just high random unitaries, now along my spatial direction. So if I look at all of these fancy distributions, actually what I end up with is I can just think of this as this kind of distribution, which is just kind of a rescaled Porter-Thomas distribution in your Temple-Hilbert space, which is essentially the space that your spatial evolution operator is acting on. So just to kind of rephrase this, we have an initial structured state, which very quickly becomes statistically indistinguishable from a high random state if you look at all of these properties into how this kind of spread out over your full Hilbert space. So this state, essentially, just look at global properties, you cannot tell that this is a structured state. The way this acts is that essentially you have randomness in your spatial direction, which you get by essentially looking at this distribution over your full Hilbert space. This randomness along your spatial direction as time goes on, this actually gets addressed to randomness in your time direction. Because say for a single time step, my temporal Hilbert space is one-dimensional. 2 time steps is 2-dimensional. 3 time steps, this is 4-dimensional. 4 time steps, and so on. This basically grows exponentially. So you're just kind of growing the Hilbert space, in which you have some randomness in your spatial direction, this temporal Hilbert space, which very then quickly just becomes indistinguishable from just having exact randomness in your physical space. And why this doesn't happen immediately is because you have some local interaction. So it takes some time before you can actually translate this randomness back to randomness in your full Hilbert space. So what I want to say here, in the previous section, we've argued that correlation functions go to 0. Essentially, they're exactly 0 almost everywhere. On the light cone, they go to 0, which is exactly what you expect for ergodic dynamics, where we typically motivate ergodicity from chaos. Here, what we can say is that our initially structured state very quickly just becomes indistinguishable from a higher random state, and the higher random states again give rise to ergodic behavior. So even while the state keeps changing, this distribution no longer changes, and expectation values of observables also no longer change. So it's just a different way of quantifying this notion of ergodicity that we expect here. So with that, I want to move on now to the final part of my talk. But before I continue, any questions about what I've told you so far?
I guess one of the things that occurs to me is how robust, I guess you'd say, are the dual unitary behavior when the gate set is perturbed or partially randomized in some way.
That's an excellent question. I would say this is still like a very active field of research. So we have all these very nice results for dual-unitary circuits, say for the correlation functions, but also for scrambling and for entanglement growth. Yeah. And people have tried to use this as some kind of starting point for a perturbation theory to see how much of this chaotic behavior is actually preserved if you slightly move away from dual-unitarity. And this is kind of motivated by so-called classical axiom A systems, which are kind of classically maximally chaotic systems, where you can make some statements about structural stability of chaos. So ideally, you'd also want to argue that all this behavior that we see is stable. And there have been some results. So I think there's been some really nice work by Pavel Koch and Tomasz Proza and co-authors. I also have a paper with my student Michael on this, and there's also a paper by Kurt von Kaiserink and co-authors, where they make some statements about some stability in very specific setups. But I would say that the general theory is still lacking. We have some results on stability of correlation functions near dual-unitarity, where in very specific setups, they're actually stable. We have the same thing for entanglement dynamics and for OTOX. For spectral form factor, there are some hypotheses going on there. But it seems to be the case that you can find perturbations where some of this behavior is stable, but it's still something we don't have a full understanding of. One thing I can say is that for these results that we've shown here, we've also looked at what happens if you slightly move away from dual-unitarity, and it seems that you can have some stability. The only thing that happens is kind of the time scale at which this becomes random slightly slows down. Which is also something that you can very generally see the moment you move away from dual-unitarity. Dual-unitarity, they're like maximally ergodic, they're maximally, they generate maximal entanglement. It's correlation spread out maximal velocity. Anything you can kind of try to observe is going to be maximal. And so if you want to have something that's more generic, you kind of going to slow down the way in which your randomness builds up, in which your entanglement builds up. So it's kind of just an extended answer to saying it really depends on what we're looking into, but we don't have a full understanding. But thanks. So, any more questions before I move on?
No, I don't think there's any questions lined up.
Perfect. Also, just want to give myself some time to drink some water. So,
good idea.
I think there's something in the Q&A.
So there is.
So, is there some connection to the temporally lead algebra of the Ising model? And can the unitary operators be constructed from generalization of the Ising chain? This is a very good question. And the answer is yes. So we have the Ising chain. So if we have, we can extend this to say Potts models to arbitrary local Hilbert space dimensions. If you do this, you can again find unitary points. And actually, I have a recent paper with Austin Lamcraft in which we do exactly this. But what you can also do is basically these models also have integrable points. So I've kind of emphasized that generally they are chaotic. We can also fine-tune them to find points in which these are actually integrable. Then we can also use the entire machinery from integrability, for example, temporally lead algebras, to also represent this in this way and study this in this way. So yes, there's definitely some connection. And we can also generalize this to say higher Hilbert space dimension and like higher generalization of the Ising chain where you can again find both chaotic and integrable points. Thanks.
Good question.
Okay, so now for the final part of my talk, I want to briefly highlight some things that people have recently been doing on extensions of dual unitarity. And it's based on a very, very simple observation that if I look into this space-time duality or the space-time symmetry of the Kicked-Ising model, I can exchange space and time, and things behave the same way, which is very clear because if I look at my unitary evolution operator, it's a square lattice. I can rotate it by 90 degrees, nothing changes. Then can we try to realize other space-time symmetries and find other either Hamiltonian realizations through Kicked-Ising dynamics, or by choosing some by choosing some appropriate gates, can we realize some different space-time symmetries, in which we can still use this kind of notion of space-time duality to solve this? And the answer is yes. I think it's a very active field. I'm kind of excited to see where this is going to go. For example, I can take these operators and arrange them on a so-called honeycomb lattice. So again, the horizontal direction is your spatial direction, the vertical direction is time. So basically what you're doing here, first time step, you're not doing anything to say the even sides. You're applying some kick to the odd sides. Next time step, you're basically applying some Ising interaction to even bonds, but not to odd bonds. Then you just act with your kicks everywhere, and then you kind of keep alternating this. So you can think of this as being some complicated protocol where you kind of only either kick or apply Ising phase to specific sides, but you can realize this in space-time through, say, some Floquet protocol, and you're going to realize this honeycomb lattice. Or you could realize, for example, this kind of triangular lattice, which is slightly more complicated, but you can still realize this. And all of these now, instead of having this space-time duality, which you can rotate this by 90 degrees, now essentially you can rotate these by 120 degrees, and you still get the same thing. So now you basically have this threefold or sixfold symmetry, where if I look at correlation functions, they're not just going to be zero exactly on the edge of the causal light cone, which was this consequence from dual-unitarity. We can actually look at what happens there. And we now essentially get three light cones. We're now basically only showing this like in one quadrant of my spacetime. So I again have the operators playing with maximum velocity along the edge of the causal light cone. But now I can also have operators just say put and don't propagate. So now I basically have this light ray with maximal velocity, but also have like a world line where operators or correlation functions just decay. So these we can all realize now as circuits. We can also all realize it as Kicked-Ising dynamics. And we can kind of realize richer behavior, where instead of having this single light cone that we get in unitary circuits, we can systematically reintroduce kind of more light rays in the hope that at some point we can actually discover like fully generic behavior and kind of fill this causal light cone. So one other example I want to give, because people have also kind of naturally encountered this, and you can again naturally realize this in Kicked-Ising dynamics. So again, we alternately apply kicks to your even sides, Ising attracts to your even bonds, and you just alternate between odd and even. If I do this, I can realize some kind of space-time diagram that looks like this. I can now kind of contract this, and I can see that if I merge these kind of delta tensors, locally this kind of returns my square lattice, which is what I get from dual-unitarity. But globally, it's giving me something very different. So what we can also do is by kind of tuning these gates, we can realize very non-trivial space-time transformations, which then allows to kind of probe dynamics in different ways. So we expect very different correlation functions, which should be some kind of almost Lorentz transformations of the correlation functions in original dual-unitary circuits. So one thing I just want to briefly mention before I conclude is that one of the main things that people have done in these kind of extension of dual-unitarity is calculate so-called entanglement line tension, which is one way of quantifying operator growth or many-body dynamics, which I take my unitary evolution operator, which here, this full lattice I just represent as this massive blue blob. And I take some subsystem A here at the bottom, so initial time and final time. And I just kind of partition this across some cut in space-time with some slope, which is some velocity. And there's a so-called entanglement membrane theory, which tells you that if I look into some kind of cut, x equals vt, where v is the slope or the velocity, this entanglement should be proportional to time with some slope, which is known as entanglement line tension. And essentially, if you know your entanglement line tension, you know almost everything you want to know about operator dynamics and entanglement growth and operator spreading, because this underlies entanglement membrane theory, which is kind of the effective theory we have right now in understanding the dynamics of entanglement. This is something you generally cannot calculate in many-body systems, because essentially calculating this is as difficult as just solving your full many-body problem. But in all of these extensions of unitarity, we can actually calculate entanglement membrane, or we can calculate disentanglement line tension, and we get some very nice results. Okay, I'm not going to go into this just in the interest of time. But if you look into how this entanglement changes as you change the slope, for dual-unitaries, this is basically just constant. It's maximum entanglement velocity everywhere. For these triangular or honeycomb lattices, you can get this entanglement line tension, which grows linearly, but it's now non-trivial. For this shear squared lattice, we can get something that's non-trivial. But what I want to kind of emphasize here is that we have this entanglement line tension, which kind of sets the full entanglement or many-body operator dynamics. And by tuning this geometry of the lattice, we can tune entanglement dynamics, we can tune the operator dynamics. For example, we can use this to tune the entanglement velocity, which sets kind of the rate of entanglement growth across some bipartition. We can use this to tune the butterfly velocity, be either maximal or not. And in this way, we can kind of extend this phenomenology of unitary circuits, which again have maximum entanglement velocity, maximal butterfly velocity. We can kind of move away from these limits and realize something that's still analytically tractable. So with that, I actually want to go to my conclusions. So in these unitary circuits, or these general unitary easing dynamics, we have exactly solvable dynamics, where I just highlighted now that we can solve correlation functions. We can also solve entanglement. We can also solve autocs. And they are maximally chaotic. So you can make analytic connections with random matrix theory, either by looking at basically spectral statistics or how your state delocalizes in Hilbert space. We can extend this notion of dual-unitarity to so-called multi-unitarity, which are these circuits that are unitary in different directions. We have different lattice symmetries that lead to still solvable dynamics and chaotic dynamics that we can kind of tune. And what I also do, I can realize all of this as either kicked easing dynamics by thinking of these as just Floquet models, or I can also realize this through an appropriate choice of gates and realize this in current digital quantum simulation setups. So with that, I'd like to thank you all very much for your attention, and please let me know if you have any additional questions.
Thanks, Peter. That was really, really interesting. I think it's fascinating. I don't see any other questions there, but just an observation. I think it's really fascinating how intimately the chaotic behavior is modeled by the solvability of these systems. Can we say anything more general about the origin of chaos then?
So I think the general origin of chaos is we try to think of this as just generating kind of evolution along spatial direction.
Yeah.
And then if you want to kind of explore your Hilbert space, you're always kind of probing some different sequences of like spatial operators. And these basically then you have some kind of randomization going on there. So it's a very vague answer because I don't have a very succinct answer. But it's really that if you look into quantum chaos, you essentially generate some randomness somewhere. Through structured dynamics, you never generate actual randomness along your time direction. But actually all physical quantities that we look into, they're somewhat averaging over your space direction. And by averaging over your space direction, there you can get some randomness, because essentially that's where you can kind of replace some summation of quantities to the appropriate average. And what we see in all these chaotic cases is that you have these unitaries along your spatial direction, and these are essentially as random as you can want. Basically, this is saying that these form some kind of universal gate set, so sampling unitaries in space, you can really generate any kind of unitary here. So also I should say, at the integrable point, this breaks down, because then you no longer have this universal gate set, and you cannot replace this sampling. So this is kind of on the level of looking into, say, statistics of something where you average over space. The other thing I could say is that if you look at, for example, this calculation of spectral form factor, yes, here. So basically, this linear growth of time, it's really the only consequence there is if I calculate the spectral form factor, this is basically, it's translation invariant in the time direction. And essentially, this translation invariance in the time direction is the only thing that survives. If you do kind of the averaging over, if you take an infinite system and you do kind of this order averaging there. So essentially, the time translational symmetry that you have is the only thing that determines this linear growth. And it follows from this kind of calculation where you calculate this using the evolution along your spatial direction. you kind of identify some transfer matrix in the same way that we've kind of identified a unitary gate. And you again just look at kind of the middle symmetry associated with this transfer matrix. So I would say it's a very hard question to answer because all these different proofs of quantum chaos, they really depend on the kind of observable that we look into or the kind of signifier of quantum chaos that we look into. But in all of these cases, we were able to make statements about general attributes of quantum chaos by translating that back to say some kind of evolution in space and just look at the minimal structure of the spatial evolution that remains. Thanks.
That's interesting.
Somewhat convoluted answer, but I think there's more questions.
Yeah. Well, was there any more questions? Did
I think Murray raised his hand. I think was
I thought Peter Drummond did. Peter, did you raise your hand and want to ask a question?
I wasn't sure if there was any time for that. I just had a very quick question. If I give you a random initial state,
Yes.
can you compute its time evolution exactly?
With random initial states, okay. I would say for generic initial states, we cannot do that. So one special thing also is that all of these states that I've talked about so far, they preserve unitarity along the spatial direction. If I take a generic state, this is not going to be the case. So people have also studied basically what happens if you move away from more generic states. And we can still make some statements kind of close to these states, but for generic states, we can't really say anything.
Okay, but there is at least one state for which you can compute the time evolution of that state exactly. So,
yes, so
in that case, what is the fidelity of the quantum computer realizations to the exact solution?
Oh, that's a very good idea. I don't know that. I think this is something that's kind of implicit in this error mitigation, where you just kind of rescale things by the fidelity of what you expect if there's no dynamics. But I don't know.
Okay, thank you.
Yeah.
Thanks,
I just want to point out, like, one of the very nice things about discrete Ising dynamics is that the states that preserve your like spatial unitarity, they're very natural states. They're basically, you have your states in your Z basis, so basically just computational states 0, 1, 0, 0. You also have states in your X and Y basis. So here you kind of natural product states that people work with happen also to be so-called solvable states for this model.
Oh,
thanks, it was a good
that's
question.
interesting. Yeah. All right. Well, thank you. I don't think there's any more questions. Thanks very much again, Peter, for a fantastic talk. I'll just remind everybody that we'll let you all know as time goes on any future talks that are coming up. And if you have speakers that you'd like to hear of, please don't feel any worry about sending myself or Murray an email to suggest any speakers that you'd like to hear from as time goes on. Those suggestions are always very welcome. Thank you very much, everyone. Thank you very much, Peter. Have a good day. And we'll talk again. Okay. Bye for now.
Bye.